Let's begin. Good morning for all. So now, are you listening? Yes. Now we are going to begin this session. So I invite Dr. John Hamlin to speak here. Dr. John Hamlin is a full professor in physiology in the University of Maryland. And his work is on endogenous warbine. He discovered endogenous warbine, and now he is going to talk about the endogenous warbine and warbine in pregnancy. Thank you.
Okay, thank you very much for that kind introduction. Are there any mothers in the audience? This one's for you. Let's see. Fortunately, I brought a pointer. All right. First, I want to thank all the organizers for inviting me. I want to thank the Pope for the fantastic weather. The weather is so beautiful here. A nice warm but not too hot day, a nice cool evening, and good sleeping at night with the windows open if you want. Okay, so pregnancy and preeclampsia. As you'll see later on in this talk, I got dragged into this area because I wanted to avoid pregnancy like the plague. Now, having said that, I have my own kids, so I've practiced the initiation factors and dealt with the offspring. But in terms of actually studying pregnancy, as you'll see in a minute, it's such a complicated, I wouldn't call it a disorder, but certainly women start off as a different species than men, and then when they become pregnant, they become yet another species. And when you see the changes that I'm going to present to you, some of the changes are absolutely mind-boggling. And the fact that there are all so many of them and so tightly orchestrated for a successful pregnancy makes every childbirth to me look like a miracle, actually. So it really is a fantastic area to study if you don't mind being frustrated all the time, because a lot of it's quite difficult to understand. Okay. So I promised Jose I would tell him. So for those of you who may not know, Baltimore is here. This is Washington, D.C., Philadelphia, and New York. So we're pretty good if you need access to any of the major airports. First of all, we have a major airport in the Baltimore area, but there's one in D.C., there's one in Philly, and there's one in New York. And I actually, for this trip, I took the train to New York because the connections from Kennedy are better than the connections that I could get from other airports locally. Okay, so now, if you're driving in this area, the Baltimore area, and you're commuting in the morning, doing whatever, you may have seen a vehicle like this with that number plate, Warbine. Okay, so this was some time ago when I looked a lot younger than I do now, and I certainly didn't have quite as much real estate in the front. But so this for the car buffs. This was a Ford Taurus, but it was unusual for a Ford in that it had a Yamaha V6 engine in it with variable valve timing controlled by a computer, and also variable intake length. So the intake lengths for the induction system for the fuel would actually lengthen when the engine was at low RPM to give it high torque, and then they would shorten at high RPM to give it high horsepower. So this was a very fast car, and for many years I was the fastest driver on the interstate into Baltimore every morning and the fastest driver coming home. It was a great car to have. I don't have it anymore, unfortunately. Like other Fords, certain parts of the car proved less reliable than the Yamaha engine that I had in it. So I got rid of it eventually. Okay, so this is a shot of downtown Baltimore from the air. And this is the Inner Harbor area, the University of Maryland. Most of it is in Baltimore is here. And over in this direction would be Johns Hopkins, where Regini is currently located. And my office is in the corner of this building, and I look out onto a cemetery where many, many years ago, when the University of Maryland Hospital started up, they buried people that didn't have, that were poor and didn't have people to take them away and have a proper burial. So I look out onto the cemetery here, which always reminds me, about life and death every day when I go in. Okay, so regarding the Pope, this is a guy called George Burns, who was a stand-up comedian in the United States. He's a straight man, and he's renowned for his one-line quotes. And so this is one: the secret of a good sermon is to have a good beginning and a good ending, and have the two as close together as possible. All right, so I'm going to try my best to have it. We'll have a good sermon, and we'll see how close I get to that. All right, pregnancy, the final frontier. Baby in the tummy, it's all up to mummy, but once the baby's had, it's bragging rights for dad. Unknown who said that. So the world population in 22 was 7.95 billion. So you can see pregnancy is a pretty popular pastime with an enduring legacy. I mean, that's amazing if you think about it. Almost 8 billion successful pregnancies, which is even more remarkable when we see the changes that are going to occur physiologically. And here are some of them. So there are major changes in the cardiovascular system. There's an increase in plasma volume, cardiac output, stroke volume, and heart rate, decreases in serum albumin, coagulation factors are altered. There's compression of the inferior vena cava, especially later in pregnancy as the fetal placental unit gets bigger and bigger and impairs venous return back to the heart. And then, of course, the body starts to compensate for that by raising blood pressure, and you get towards a state of preeclampsia. And what's going to happen is you have to lay the mothers down, or the expecting mothers down, so that you don't have this problem with venous return. So that's where the idea of bed rest comes from. And then there are changes in the liver with metabolism, changes in the lungs, in tidal volume, changes in the stomach. There's sometimes nausea and vomiting. I don't know if any of you have had that. Yeah? Oh, yeah. Delayed gastric emptying, prolonged small bowel transit time, GI reflux. All these things can sort of happen. And so that's a sort of bewildering start, but it actually gets worse. So when you look at it from an endocrine aspect, the first thing you see is that all the salt and water retaining systems in the body are activated. So ACTH is switched on, renin is switched on, there's more angiotensin II, there's more aldosterone, cortisol, and vasopressin circulating, and all those drive renal salt retention, and there's increased levels of endogenous cardiotonic steroids. I mean, why not join the club? Everybody else is in, let's just go. And then on the other side, we have elevated progesterone, estradiol, prolactin, human chorionic gonadotropin, relaxin, and at labor, we have an increase in oxytocin. So it's a bewildering number of endocrine changes. If you have any interest in endocrinology, it's absolutely amazing what happens here. And then conversely, there are salt-losing systems that are turned down. And one of those is the atrial response to stretch of the cardiac atria, and you get less AMP released. So the result of all this in combination as you go through weeks of gestation is you see a large increase in plasma volume, up to 50%. Cardiac output goes up a lot, and all these things return to normal after delivery, fortunately, in most women. Now, there are blood pressure changes during pregnancy. So a successful pregnancy is given by this red line here. So typically what happens is during the first trimester, blood pressure falls. And during the second trimester, it may start to creep up a bit. And then in the third trimester, it'll come back roughly to normal or slightly above normal. And that's a normal, successful outcome. So the decline in blood pressure that you see here is due to active vasodilation of the vasculature. That's the initiating event. And the decline in blood pressure that you see would actually be much greater were it not offset by protective increases in sympathetic nerve activity mediated by the arterial baroreceptors. So they stop this thing from going too low because that would be bad, but they allow it to go down just enough so that we have a much faster venous return and cardiac output. And this is actually depicts sympathetic activity in pregnancy. So this is pre-pregnancy, and you can see the increase in sympathetic spiking as you go towards term. And then postpartum, it comes back. So that's a huge change. Now, we get to the more interesting part of this, which is the progressive increase in endogenous warbane during pregnancy. So what you see here, ladies before pregnant, then they become pregnant through the first trimester, the second trimester, and the third, and you'll see there's a progressive increase. And this is a study by VIII out of Helsinki, published in 2000. And then after delivery, so this is a normal uptick in endogenous warbane. After delivery, over time, the warbane levels go back to normal. And in some studies, there's a relationship between the systolic blood pressure and the amount of warbane in the blood in those women. Okay, now I want to point out a couple of things here. So back in 2000, the study was published that sort of reviewed all the immunoassays and various assays that have been used to measure endogenous warbane. And in particular, what you see is the cross-reactivity of the various antibodies. Most of them are highly warbane selective. There are no antibodies that are warbane specific. In fact, there are no antibodies anywhere that are specific for their target. They're just selective. They all have cross-reactivity to something, right? It doesn't matter what antibody you use, it's never totally specific. If you jack up the cross-reacting entities enough, you get a big signal. And the importance of that is that in pregnancy, remember, all the typical corticosteroids and the ovarian steroids are elevated. So even though you have an antibody that has seemingly very little cross-reactivity with any of those, if those things go up 10, 50, 100 times, then some of these might get to be problematic in the assay of endogenous warbane. Okay, so I made my point. Now the other point is that most of these studies report plasma levels in the low to mid picomolar range. Okay, so we're not looking, rarely are we looking at things in the nanomolar range and never in the micromolar range because of course they would be lethal. All right, now the hemodynamics of pregnancy, which is actually how I got into this. So the initiating event is arterial vasodilation. That vasodilation event is controlled by the mother, and it results in a decreased vascular response to all the vasopressor hormones, including angiotensin II and norepinephrine. There's an upregulation in prostacyclin, which is a dilator, and this enhanced nitric oxide production. So these are the factors that drive the decrease in total peripheral vascular resistance that you see in the pregnant woman. And then the drop in afterload triggers baroreceptor activity that I mentioned, which increases the cardiac contractility and the heart rate. And then in addition to that, there's increased mobilization of venous blood towards the arterial vascular compartment. So all of that combined together leads to a drop in blood pressure that I've talked about. So what we have as the initiating event is a programmed hypocontractility of the arterial vasculature. All right, now we come to the situation in preeclampsia. So the problem in preeclampsia is the early vasodilation event that a normal woman would experience doesn't happen, or it's weak. And some of the reasons for that are not entirely clear. So instead of having her TPR go down, it tends to drift up through the pregnancy. And it may drift up enough that it raises blood pressure to, it can be dangerous levels, actually. So the arterial sensitivity to angiotensin II and other vasopressor agents remains elevated instead of depressed. And then typically after 20 weeks of gestation, the diagnosis of preeclampsia is hypertension and proteinuria. So you can see that the kidneys are affected. They start to get leaky and more protein appears in the urine. And there's a generalized vascular leakage of protein around the body. It's not just in the kidney, but elsewhere. The result of this drop in cardiac output is there's a decrease in placental blood flow. And that means there's intrauterine growth restriction. So the children of preeclamptic women are going to be smaller. That affects about 5 to 7% of pregnancies, and preeclampsia is the leading cause of maternal and fetal morbidity and mortality. All right, now, there have been a fair number of measurements looking at endogenous wildbane and MBG in human pregnancy and or preeclampsia. The first 4 of these, I'm not going to talk about them in detail, but the first 4 use a radioreceptor assay. It can be using red blood cell sodium pumps, whatever it is. And the last 3 use radioimmunoassays based on wildbane antibodies or MBG antibodies. What all these groups see, they're all independent groups pretty much in different countries, they all see the same thing. They see elevated levels of endogenous wildbane going progressively up through the various trimesters, right? And then coming back to normal afterwards. And in the preeclamptic women, the rise in wildbane is much faster and goes up much higher. They all say the same thing. So the main takeaway is EO is typically what we call super elevated in preeclampsia. So the question is, what does that mean, right? Is it just a bystander effect, or is it actually driving the preeclamptic state? So there are a lot of people that think it's a driver of preeclampsia, and I was in that camp. Because, as you know, endogenous wildbane's got a profound vascular action that enhances contractility. All right. So other people wondered the same thing. They had the same idea, is this important or not? So the way they addressed it was to give digoxin binding Fab antibodies to women who actually had severe preeclampsia, and they tried to see what happened. So this was a study done by David Adair. It was published in 2010. And the bottom line is that the antibody fragments slowed the decline in renal function and also reduced blood pressure in the preeclamptic women. So it had an impact. Now, the thing about digoxin Fab fragments is they're highly selective for digoxin with about 10 to the minus 11 affinity. But they also bind endogenous wildbane with nanomolar affinity, and they bind MBG with about 10 to the minus 8 molar affinity. So the experiment worked in the sense that blocking something that binds to these antibodies was effective here clinically. All right, and then there was a follow-up to it based on the same thing. So they said, does DIF treatment improve the maternal and perinatal outcome? So yeah, we had a benefit in the mother, helped the kidneys, and it helped blood pressure, but did it mean anything else? And the answer was yes. So it turns out the antibodies also improved maternal and neonatal outcome. Okay, so what you see here is, first of all, it attenuated the decline in creatinine clearance, which is GFR, and that's quite a dramatic difference, minus 4.5 mils per minute versus 53 mils per minute. in them. And it also reduced the rates of pulmonary edema. Only 1 out of 17 versus 6 out of 19 women got pulmonary edema. And if you looked at a neonatal intraventricular hemorrhage, the women given antibodies didn't have any hemorrhages at all, whereas 5 out of 19 did. So those 2 very highly statistically significant results. So after that, oh, I seem to have stopped. Oh, okay. So I can't seem to get to the next slide for some reason. Let's try that, please. We're frozen. Ah, there it comes. So, like a lot of things in my life, its direction was influenced by other people. So this lady showed up in my lab with an idea that she wanted to study preeclampsia. Here she is. This is Brandeis Jacobs. And yeah, that's working nicely. Hey, I want to do my thesis in your lab. I want to study pregnancy, Wabane in pregnancy. Okay. Ave Maria. No, pregnancy, no. Hypertension, heart failure, renal, anything, but not pregnancy. Please, not pregnancy. So I said to her, go and see Dr. Thompson, who worked in obstetrics and gynecology. He had a lab. He's studying fetal hypoxia. To get fetal hypoxia, you've got to have pregnancy. And, you know, it seemed like a real good lab for her to go to because she was real interested in that sort of thing. Not happy. So anyway, she goes to his lab. There he is. And she decides to do a 3-month rotation there. So she's trying to decide which lab she's going to do a PhD in, basically, okay? And as you saw, I said, no way, you're not doing it in my lab. And 3 months later, I didn't like the Thompson lab. Okay. Try another lab in OBGYN, right? So she disappeared for another 3 months, and I thought, she's gone for sure. No, she's back. So that was the beginning of the end of that for me. So anyway, so we started. So this is a quote from her. So again, so I was ready to uncover the single underlying mechanism of preeclampsia and write my Nature paper, all within the timeline of the rotation, 3 months. Talk about, well, what can you say? I mean, all I had to do was create a rat model to study preeclampsia. Now, it turns out later I'll show you there is a rat model of preeclampsia, but we were going to try and create a model just based on excess Wabane because we thought that was the important thing. So it was an absolutely mind-numbing, simple hypothesis. What we knew is that elevated circulating levels of endogenous Wabane or Wabane raise total peripheral vascular resistance and drive hypertension in normal males and female rodents. Okay, so the idea was then by Occam's razor, the super elevation of EO in the preeclamptic women presumably is a driver of their vascular resistance. Right, so then the idea was that EO and PA in preeclampsia was likely to be abnormal and potentially pathological and a stimulus to the underlying TPR. So the working assumptions were these. This was, of course, verified. And then this was the question. And then if that was going to work, then did it activate the same mechanism we saw in non-pregnant rodents? So I sent her off to the lab. And I said, let's get some osmotic pumps and pump these pregnant rats up with Wabane, super elevate the blood levels, check the blood levels, and find out what happened to blood pressure. Wabane would not induce hypertension in the pregnant females at all. So she came back, she said, it didn't work. Try again. And again. And again. And again. Okay, I wanted to be absolutely sure about this. Now, we weren't doing huge numbers of rats in this study. You know, we'd have 3 or 4 pregnant, and we'd bung some wildbane in them, and then we bung some wildbane in non-pregnant animals, and they got hypertension, of course. So that was the comparison, and we did enough of those eventually where we said, enough already. Another Ave Maria moment. So the first basic working assumption of this plan of hers was in the toilet, so to speak. It just wasn't going to happen. So the plan seemed to be turning out really, really badly. And I thought, you know, this is why I didn't want to get into studying pregnancy at all. But it turned out that it wasn't going so badly, but we didn't realize that at the time. So the first thing we needed to do was to confirm that we could super elevate wildbane in rat pregnancy. So these are non-pregnant animals, and it was about half an nanomolar, and then the pregnant animals got more. And then if we superimposed a wildbane infusion on the top, the non-pregnants got obviously a lot higher blood levels, and the pregnants went way up. So we definitely had a super elevated state. But when we looked at the blood pressures, so these are the blood pressures. So these are non-pregnant rats. They get hypertension over 20 days with a wildbane infusion. These are the control rats. They get vehicle. And these are the 2 pregnant groups, with and without wildbane super elevation, right? And what you see is they get a nice dilation and lower blood pressures independent of the super elevation of wildbane. So that was a bit of a shock to us. So then we said, is endogenous wildbane really elevated in pregnancy? And the reason for that is, you know, it turns out that this is a radioimmunoassay, and as I mentioned, there are no antibodies that are absolutely specific for their ligand. They're all selective, but they have cross-reactivity. So what did the RAA actually measure? Could it be that all those other studies picked up cross-reacting steroids from the adrenal and the ovaries? So, so with this in mind, we went to, okay, I need to go back a bit there. So this is the basic working plan. We take plasma. You have to extract the plasma over some solid phase matrix to clean it up, and then you send it for radioimmunoassay, and that's the result that you get that I just showed you. So then we said, okay, let's take that same extract that we used for the RAA, and now we'll subject it to HPLC. We'll separate out the peaks, and then we'll redo the radioimmunoassay to find out where the main cross-reacting peaks are. And the answer that you get looks like this. So this is the HPLC of wildbane. It's a very slow polar gradient. Endogenous wildbane is here. Digoxin would be about here. Most of the adrenal and ovarian steroids would be here, and MBG is somewhere in that region too. So in this area, really, there's nothing else that's likely to cross-react. Okay, so now we do the radioimmunoassay again, and what we find is in the non-pregnant animals, there's a peak at, this is at 35 minutes, which is where wildbane elutes. Okay, and we see some other cross-reacting peaks. This is where dihydrowildbane and warbagenin would elute. So there's a little bit of something going on there, and then there's some other peaks later on. Don't know what they are. But the important thing is that in pregnancy, the main peak is elevated, right? So that's pretty good evidence. But again, it's not a complete proof. And also in the pregnant animals, we saw something late here that was detected a little bit later in the gradient that I'll show you later proved to be an isomer. All right, so now we turn to mass spectrometry. And in mass spectrometry, we do what we call a full scan, where we look for the parent ions of endogenous wabane. And you actually can't see them here because the amounts are so tiny, they're obscured by the background. But because of the miracle of, this is an ion trap, I can actually isolate any ions that are in there that are at the appropriate mass to charge ratio. And then I can take those subsequently and fragment them, and I can see what they call the MS product ions of endogenous wabane, or wabane, which is here at 445.2. And we put an internal standard, which interestingly is dihydrowabane, which is 2 mass to charge units greater. And we use that to calibrate the data that we get. So most people would stop here. So we have an LC separation with MS after it. But we don't stop there. We take these MS ions, product ions, isolate them, all right, and then put them into the third dimension where we apply collision energy again. And now we get this beautiful, actually, spectrum. And that spectrum blown up looks like this. And what you see are pairs of ions. So here's the endogenous wabane, and here's the dihydro reference. 1 water loss, 2 water loss. We can see the loss of the lactone ring in the 2, and further losses. Typically, we're going to use this peak for quantitation and compare it with this peak as the internal standard. But the point about this is that when you apply this method to these same fractions, what you see again is endogenous wabane. You don't see wabagenin or dihydrowabane because you're not targeting them. They're a different mass to charge ratio, so they will never appear there, okay? But what you do see is endogenous wabane, and you see this other isomer that runs a little later, what we call isomer 2. Now, when you look into pregnant animals, what you find is another peak, which we term isomer 1, which we've seen in other scenarios related to angiotensin 2 excess. But you also see this massive increase in the second isomer. So just look at this. This is 100 picomoles or something per fraction. This is 8,000. Going from almost nothing here to 8,000. That's a massive, massive change. Now, we don't know exactly what that isomer is or what it's doing, but it's there. But the important point is, again, we see the big uptick in endogenous wabane. So this is beyond any reasonable doubt that any analytical person could have. We've definitely targeted that, and we can show it is really elevated in pregnancy. So that was something that we needed to do. All right, so we have the first proof that EO per se is elevated. The first evidence that elevated EO or super elevation won't raise blood pressure. So normal pregnant rats are protected against hypertension. And then the next question is, you either run away from the project or you try and figure out what happened, right? Why are they resistant? And that leads into what we think is the chronic pressor mechanism of wabane, at least I should say the vascular pressor mechanism, because there's a CNS mechanism as well that's independent. Is that sequence altered? So here is the normal sequence as we understand it. Elevated wabane in the circulation binds to alpha-2. You get a decrease in alpha-2 pump activity, transient. You get increased phosphorylation of SARC. SARC then comes along and by some miracle of things we don't really understand, increases the expression of NCX1, which is going to bring calcium normally into the vascular wall. It also upregulates the expression of alpha-2. The upregulation of NCX1 triggers the upregulation of TRP channels that bring calcium and sodium in, both TRPC3 and TRPC6. And together, the combination of this brings more calcium in, raises signaling and raises tone and blood pressure. So that's the key events that we believe happen in a normal non-pregnant female rat or a male rat. Now, when you start looking in pregnancy at the different ion transporters, what we find is alpha-2 pumps are reduced in the aorta, but not in the mesenteric arteries. Okay, it's just the way it is. If we look at NCX1, 1.3, it's reduced in aorta and mesenteric arteries. And if we look at 4 other iron transporters that we think are important in the mesenteric arteries at the top or the aorta at the bottom, we find, surprisingly, no change at all. So the changes that we see are just in alpha-2 and NCX, basically. It's kind of a big shock to us. So how about alpha-1 pumps? Alpha-1 pumps are down in both the conduit in the aorta and the mesenteric arteries. And this is just a simple summary table. The bottom line is this. It looks like the whole basis of the vasodilation in the mother is actually due to a drop in NCX and a drop in calcium influx. So that would be the initial vasodilating event. Now, what happens in pregnancy? Pregnancy switches off. So all these upstream events happen. SARC gets phosphorylated, but the link between SARC and NCX1 is switched off. It's broken in some way, and it's broken by pregnancy-related drivers. Okay, so none of these things then that you see here actually happen, and instead you get reduced calcium entry and you get a dilation. All right, so normal pregnancy, a high EO state, 2 novel isomers of EO that become elevated, superphysiological concentrations of warbane don't do anything. The chronic vasopressor effect is switched off, so the mother and the fetus are thereby protected. And then in small arteries and arterioles, only expression of NCX 1.3 was reduced. So reduced calcium influx, and that's actually not been tested, but it almost certainly has to happen, explains most of the functional decline in vascular tone and BP during pregnancy. So then the question is, what's next? What switches on the vasodilation? What switches off the pressor mechanism of EO? Are they the same switch? Is the vasodilation switch maternally or fetally controlled? Okay, are the isomers controlled maternally or by the fetal placental unit? What do they do? And what about preeclampsia? Why is EO super elevated? Is it helping or hindering? So normally when we see elevated levels of EO in heart failure or hypertension or renal failure, the outcome in those patients is much worse. So the expectation is like we started, that in preeclampsia, the super elevation of warbane is actually harmful. So we decide to test that idea. And that's important because it's going to determine whether blocking EO, right, versus raising EO is likely to be of therapeutic benefit in those patients. Now, during normal pregnancy, there's remodeling of the spiral arteries that are going to provide flow to the placental unit. So they go from having a fair amount of resistance in them and a large smooth muscle component here. They get remodeled by the trophoblasts, which invade the spiral arteries, and they don't really kill the smooth muscle cells, but they end up replacing them. So you go from an artery that was muscular and contractile to one that's just a conduit. So it dilates, and then because it's so large and has no real contraction anymore, it's able to flow very large amounts of blood to the placenta. So that's what happens in normal pregnancies. In preeclampsia, for reasons that are not understood, the trophoblasts invade the spiral arteries, but they don't properly remodel it. So it never becomes a big conduit like it would in a normal woman. And that inability is linked with overexpression of this soluble tyrosine kinase S-FLIP1. Okay, so now, since warbane won't induce preeclampsia, we started looking at other models, and there's a Rupp model of rodent preeclampsia. And so what you have is this arcade, the left and right arcade. So these are the ovaries, and then this will be the blood supply to the placenta, which comes down here and through these branches. So you put clips on the arteries, right? And that reduces flow to all the little babies that are going to be here by about 40%. So it mimics what you see in a preeclamptic woman. And you can a comparison has been made of the characteristics in women with what they call the RUP model, which is reduced uterine perfusion pressure. And what you can see is in virtually every parameter you can measure is reproduced by the model. There's one difference. Where is it here? Somewhere. There. Abnormal placentation. Obviously, in the model, you start off with a normal placenta and then you add the clips, right? Whereas in the women, the placentation process itself is faulty to start with. So you don't quite reproduce that, but that doesn't really matter. And then everything else is pretty much the same. There's some difference here in glomerular endotheliosis. You see that in women. You don't see that in rats. You see podocyte shedding from the kidney. It doesn't seem to have been measured in rats. And the HELP syndrome, which is hemolysis, elevated liver enzymes, and low platelets, you only see in the most severe cases of preeclampsia, and they're going to go on to full-blown eclampsia. So that's really a bad thing. So you don't see that in the RUP model either because it's just not severe enough. Okay, so this is a study done by Rana et al. It's published in 2014, and they're asking the question in the RUP model of preeclampsia, if I add Warbane into the circulation to super elevate it, do I get a benefit or do I cause more harm? And what you find out is if you look at SFLT1, remember SFLT1's driving the abnormal placentation, typically. What you find is that 5 nanomolar Warbane actually knocks SFLT1 down. In other words, it's beneficial, seems to be beneficial. All right, so they go on a little bit further, and now they study this in primary cytotrophoblast cells and in the villus explants. And it's the same story. Warbane in the nanomolar range suppresses all the indices that would be harmful in a sense. So this is a sort of a big shock. And I'll skip this in the interest of time. I'll skip that one, but they all say the same thing. So the impact of super elevation of Warbane in these mice with RUP is their blood pressure is lower. Okay, the number of pups and the weights are similar. And there's an improvement in these various indices related to oxidative stress and so forth. So this is a bit of a surprise. So the conclusion is that super elevated circulating levels of Warbane in this model of preeclampsia seem to be beneficial, not harmful. So that's the exact opposite of our initial working hypothesis, right? So that's the way life goes. You don't always get what you want. And then the question is what's the mechanism? Is it an anti-inflammatory action of Warbane, which some people see in certain paradigms? So what we think is the elevated EO in preeclamptic women is a normal beneficial physiological response. And as I said, that's the opposite of our working hypothesis. So what's it doing in pregnancy? Well, there's 3 interesting papers. 2 are by Anita Piria's lab that show that Warbane protects against adverse developmental programming in the kidney. Okay, so there's 2 papers about that. And then there's one by Devela Levitt and David Lichtenstein's lab. A reduction in maternal circulating Warbane impairs offspring growth and kidney development. All right, so it looks like the lack of EO in pregnancy is a bad thing. It's a bad thing particularly for the offspring, and presumably that's an epigenetic effect. And here's another interesting result, again from the Lichtenstein group. If you look at infant birth weights, right? So some babies are big, some babies are small. So the big babies are associated with elevated levels of endogenous Warbane in the circulation, whereas the smaller babies have lower levels in their mothers. So it looks like Warbane is actually a growth-enhancing factor for the fetal placental unit. And that's probably why that's one of the reasons I think we have it. So the bottom line is the progressive increase in EO we think is beneficial. Low EO in gestation is linked with low birth weight in rodents, appears to have long-term negative consequences for the kidney and heart. Maneuvers that lower interfere with EO in normal pregnancy would appear to be contraindicated. Let's leave normal women alone, right? And if we're going to do something, maybe maneuvers that interfere with ECTS in women appear to be beneficial based on what we know about the DEEP trial at the moment. Okay, so here we are now. All's well that ends well. We both survived, much to my chagrin, and her other thesis project was a success. And I should point out, just to stop any speculation, none of my genes are in her offspring. Okay, so that's the end of this talk. Thank you very much.
Thank you for your nice presentation again. So, questions?
So, John, do you think that the increase of the endogenous globin could be like affected by the fetus? By the
So
it's a hard question, but
no, it's not.
What do you think that is more?
We've already figured it out. So it turns out that the title of this talk was part 1. There's a part 2 and a part 3, which are about the same length each, and there's no way I could get all the data in. I just wanted to get the main message over. So it turns out that the elevated endogenous globin is controlled exclusively by the mother and not the placenta or the fetus. So there's some debate. There was some interest in that question in the literature going back, but there was never any data. People talked about things in the placenta, steroids in the placenta, CTS in the placenta. Yeah, they're there, but as far as we can see, they all come from the mother. The mother's in charge, basically, of that particular thing, which was kind of interesting, because if it had been the other way around, it'd be really interesting if the fetus could affect its own development, right? But it seems that the mother is controlled. So when there's a fault, you blame the mother.
Have you tried to identify the isomer 1 and in isomer 2 and figure out what role they have?
Yeah, you know, this is not a trivial exercise. There's no way you're going to get enough rat blood to do that. And so you have to start bleeding pregnant women, which is, again, to get enough plasma to do it is not a good thing, because you're going to need probably on the order of maybe 100, 200 liters to do this, to get enough out, you know, to bring it all the way through to purity and then get it. I have an idea of what the 2 isomers are structurally, based on their mobilities and some other mass spec data that I have. So if you go further in the mass spec sequence, with an ion trap, you can go many, many more levels. You can go up to 10, actually. So when you get into MS4 and MS5, you start to see differences that are related to the orientation of the lactone and other differences in the molecule. But the problem is with that, it's all inferred. And to know exactly what the real differences are, you're going to have to get enough and get them into a high field NMR instrument and do, you know, heteronuclear NMR. And for that, you need a lot of material. So the short answer is I don't know exactly what they are, but I have my suspicions.
Wow, that was a fantastic talk.
You're always so complimentary.
No, it's true. I mean, it's fantastic. So have you looked at other aspects? So in terms of blood pressure, you know, there is a decrease, and you mainly said that that's because of vasodilation. No, and I believe that. I'm not.
Yeah.
But
that's not new. Everybody knows that.
Right. Okay. So, but what about, you know, on the kidney and, you know, these super high levels of endogenous globin? Do they have a natriuretic effect? Is the volume being decreased in some way there?
Remember, all the salt retaining hormones are turned on. including endogenous wabane,
including
which is a salt retainer at those
Right.
concentrations. It's only
Okay.
when you get to much higher concentrations do you get natriuretic effect.
And that's what I say when you
In my
talk about
opinion.
the super endogenous
elevated,
wabane. So
yeah.
what happens there? That was where
Oh,
I was going.
Well, so the levels that we create in the rat, you're never going to see in a human. But remember, the question is, or the related issue is, what's that isomer 2 doing? Because that's going from virtually undetectable all the way up to massive concentrations. And the question is, if that was binding to sodium pumps, and if that was really wabane with the same affinity, you'd be dead instantly, right? So there's something going on with that entity. And the question is, could there be other actions that influence salt and water and all the other things that go on in pregnancy? And I haven't the faintest idea. We started this thing, and as I said, it went the wrong way. It wasn't going the way we wanted it to go.
Right.
But the result of it is actually more fascinating than had it lived up to our initial expectations. But it just raises more and more questions. And there's not enough time.
No.
And money to do all these things.
No, of course. No, that's great. Can I ask another one? So has anybody looked at the effects of these super wabane levels in the placenta?
Not that I know of.
Yeah.
Not that I'm aware of, no. I mean,
Oh,
people
it's
have
very-
ground up placenta and looked for things.
Yeah.
And there's sodium transport inhibitors in there, but and people make the case that they're bad, but they might not be bad. As I say, this looks like a growth hormone to me that supports fetal placental growth and development.
Yeah. Oh,
Right?
that's
And
great.
there's human studies as well. It's not just in rodents. It's in real live women.
Mhm. Yeah, that's good. Excellent. Yeah, thank you so much.
John, I'm confused because I haven't followed these works lately, but you talk about wabane and endogenous wabane, or CTS. So how do you distinguish? Isn't it
Can't be
the same?
distinguished. They're the same.
But you said it's not the wabane, it's the endogenous CTS.
Yeah, it's an endogenous CTS. It's wabane. So we talk about, I have to distinguish between the two. So when we make the measurement of endogenous wabane in a rat, right, that's endogenous wabane. And if we add wabane into the animal, you've added wabane that came from a plant. And so they actually can be distinguished in the sense that the isotope ratios of them are actually different, the natural isotope ratios, but we can't separate those because they're a mix. Once they're in the circulation, you can't get them separated again. So in theory, they could be if we could separate them, but we can't, so we don't.
And you don't use any wabane labeled with radioactivity or something?
You could add radioactive wabane in, and you could get the problem is then how would you do the assay, right? Because the antibody's not going to distinguish, so you'd have to have, I don't know how that would be done. There's no way to distinguish them once they're together.
This is
Sorry,
what confused me.
Be
But,
nice if we
okay,
could.
so it's the same.
It's the same.
Practically.
Yeah.
Okay.
It's always nice to hear, especially when I'm not pregnant. Last time I was. I will never forget.
You're obviously a great success.
But I have two questions. One, I feel I should know the answer, but I remember in heart failure patient, there is this paradoxical vascular response to wabane that they test in the forearm. So instead of increasing blood pressure, it decreases it. I don't remember if that was true or tested in pregnancy.
Oh, it's never been looked at.
So well, maybe we should talk because
You're not going to be able to infuse wabane into the forearm of a pregnant woman in the United States. unless you want to go to jail.
That's true. Yeah, yeah.
This
So
is-
maybe that's why. Okay,
They're not
okay,
gonna, you
okay,
just can't do it.
okay. Yeah. So and in heart failure, they
What you
would-
could
yeah, that
do
would make
is
sense.
maybe associate the tone in the forearm when maximally dilated and contracted naturally. You could do it by natural means with the endogenous level. You might get a relationship. That might be feasible. Difficult, but feasible.
Okay, okay. All right. So that was the first question. The second one, I just wondered, I have no idea. Level of endogenous cardiotonic steroids, or specifically warfarin, in other types of complicated pregnancies. Have you looked at it? I'm thinking about gestational diabetes when
Yeah, right.
I mean, I think that can be addressed. The
Right.
mechanism is better known, but
Yeah.
maybe there would be something, crosstalk between those endocrine systems, because that's what
There
they
should
are.
be. You
That
think there would
maybe,
be, yeah.
Uh,
Yeah, you think there would be. I've not looked at it, but there are measurements in pregnancy-induced hypertension, separate from preeclampsia, which are two different disorders in pregnancy, and they're not the same, even though they both have hypertension. The preeclamptic woman's got a renal leak of protein, which a pregnant woman with just hypertension won't have.
okay.
Okay, so those mechanisms could overlap. Again, warfarin is super elevated in the pregnancy-induced hypertension, and there are other disorders in pregnancy, as you know, as well. And then there's eclampsia itself. And to my knowledge, none of this has been done in any of those patient groups.
Okay. Thank you.
At least in a way that, I would be comfortable believing.
Yes.
Thank you. John, you said that mother is in charge.
Mother is in charge.
Preeclampsia, it goes in the families. Is it inheritable?
There is a genetic component, but it's not that strong.
Uh-huh.
It seems to be more related to lifestyle and nutrition if you look around the world. So in poor countries where medical care is lacking and other nutritional support is not there, it's a much higher rate. So most of it's probably environmentally driven.
Mhm. Thank you.
So I also have two questions, or one question and one I'm a little maybe confused. The first is that you named this contractility of arteries or sensitivity to noradrenaline and angiotensin reduced. Do you know why?
Yeah, we think it's because of the reduced calcium influx from NCX. So there's less stored. So when you flash the tissue with noradrenaline or angiotensin, there's less to come out for the peak. Mm-hmm. Right, and then so those are evoked responses, right? They're by infusion. Actually, they've been done, and it's pretty clear that the whole vascular response is damped down. So, and we think it's all secondary to reduced NCX.
So it does not depend on agonist you use. So it's not something with.
It doesn't seem to be, as far as I'm aware, it doesn't seem to matter what ligand you use to turn on the receptors.
Another one is just I'm sitting and trying to put everything together what you present, so we need to have OBI need to be increased during the pregnancy to potentiate or stimulate the growth of fetus.
That's
right.
That's
and
our understanding.
when a preeclampsia, you have a risk of some reduced growth, and could it be this an extreme increase in a preeclampsia of OBI is kind of a compensatory.
Yeah, absolutely. I think the mother is
just attempt to.
We need more flow, so I'll drive pressure up to push more flow into the fetal placental unit. Yeah, I think it's not a bad thing. It's a good thing, but we always thought it was a bad thing because, as I said earlier, wherever we saw elevated warfarin in hypertension or heart failure or renal failure, it was associated with worse outcomes. And this is the same, actually. It's associated with a worse outcome, but it's not the cause of the worst outcome. It's actually trying to minimize the worst outcome, if that makes sense.
Yeah.
Right? So it's actually, so we were just looking at it completely from the wrong side of the mirror if you like.
Yeah, it's beautiful. I think. Yeah.
Yeah, well, this is the way it turned out. So now it's got me wondering about the association in hypertension and renal failure and heart failure. Do we have everything backwards, right? So to get answers to that, you're going to have to go into animals, and because it's hard to do a lot of the manipulations in people that we would like to do. Of course, we could give Digifab and Digibind and other things, and maybe rostaferoxin, if we could get approval for it. So, or maybe BD 8, 10, 14,
8.
BD 45, I don't know, eventually.
So your model of where endogenous wellbeing comes from would suggest to me that you going into this that you're sort of biased that had to come from the mother because there was a development. The fetus has to develop a while before.
Didn't have any bias. We just.
But your model is that it comes from a specific gland is where it's being produced. So you'd have to get to that developmental level, right?
Yeah. So the background idea is that it's of adrenal origin.
Okay.
In the mother.
And that's a late.
But the elevation during pregnancy, it was open about whether it came from the fetus or the placenta. We had no bias in.
But it would have to come from a relatively developed fetus. Before, isn't that right?
Not necessarily, because the clearance rate is so slow that the secretory rate could be handled by a few thousand cells. Actually.
How? So you think it's possible? I mean, it's possible that it could be that early of a fetus that.
Yeah, absolutely.
Okay. That would produce endogenous wellbeing.
In part 2 and part 3, which I don't show you here, we explicitly tested the hypothesis, and it's the mother.
Yeah.
Comes from the mother, which. I'd have liked it the other way around, actually, but I'm not getting what I want most of the time these days.
And so, what's your model for the hormone receptor? Is it a pump?
Yeah, it's for most of the stuff we do in rats at those circulating levels is going to be alpha 2. Alpha 1's resistant, it's not going to see those, and alpha 3 is mainly in the brain and the peripheral nervous system. So there'll be some effect on alpha 3. But most of for the vascular effect is on alpha 2.
And then there's some signaling associated with alpha 2 inhibition.
We see signaling associated with activation of alpha 2 by Y-wabing, if you want to call it activation. Yeah, definitely.
Another question?
Not really quick. It's like, so wabing will cross the placenta easily. Is there somebody check that?
It's in the fetus and it's in the placenta.
Cross it or the fetus is...
No, it crosses in. Like digoxin, in fetal heart failure, the physician will give digoxin, treat and it crosses the placental barrier into the fetus.
We definitely need to evolve cardiovascular to get into
Yeah. But like has been said here, I think by
Leora.
Yeah, Leora. Yes, you've made the point. Too much of a good thing is a bad thing, and too little is a bad thing. Sorry. Was it? Oh, it's a case of mistaken identity. So this is the same thing here, but in this case, it looks like too little is the bad thing, rather than too much.
Last question. Is my question,
Yeah.
but it's a general question about preeclampsia and the offspring. There's some consequences.
Yeah.
In the
Sure.
offspring, hypertension, for instance.
Yeah. So if you look at the offspring later in life, they tend to have more kidney problems. They tend to have larger hearts. They may have some IQ-related issues. So
this increase in the mother maybe affect the increase. This is just hypothesis. Affect the increase, like imprinting something.
Yeah, it's epigenetic. It's epigenetic effect. Most people think.
Okay.
So what happens in utero is terribly important for the future health of the offspring, and you won't see some of those health effects until second, third, fourth decade, fifth decade of life in the offspring. You don't see it right away necessarily. Sometimes you can, but typically it's delayed effects.
Okay.
it makes everything much more
Yeah,
complicated.
sure. Thank you, John.
Thank you.
Now, Dr. Liora. I'll present you
Now
first.
you hear me.
Liora, I'll present you first, just a little bit.
I said, you said now.
No, I know. I'm misleading. So Dr. Liora Shoshani, she's from the Center for Research and Advanced Studies of the National Polytechnic Institute, Cinvestav, in Mexico, and she works basically with cell division, polarization, and cancer biology. And now for a long time, she's working with the beta subunit of the sodium pump, especially in the case of cell adhesion. So thank you again, Dr. Liora.
First of all, thank you for inviting me. This is a wonderful meeting. I enjoy it so far, and I believe it will be very exciting at the end. Okay, so let me tell you what I am doing in my lab. How do I change? This is the one. Let's see. To change? It's done. And okay.
This one is pointer.
Pointer and to change.
To change this here.
It doesn't work, so I will do it.
Check now. Check.
No, nobody used it before. I think it was not working. I will change by. In my lab, we were working for the last years, many years, with the epithelial beta-1 subunit of the sodium pump. We were interested principally in the polarization of the sodium pump. As you know, in epithelia, the pump is localized in the lateral membrane of the cells. And we had an hypothesis that part of the mechanism of polarization of this pump, once it gets to the membrane, it stabilizes, it stabilizes in cell-cell contact, and this is how the pump retained in the lateral membrane. So our hypothesis was that the beta subunit of the pump is an adhesion molecule. This hypothesis was explored at the lab, and we could show that indeed the beta subunit of one cell needs to recognize first and contact the beta subunit of the other cell, and this is how it stabilizes in the cell-cell contact in the lateral membrane. This is obviously important because if the pump is not polarized in this membrane domain, the flow of sodium and all the regulation of ions in the cell is missed. So we had published various papers trying to demonstrate that indeed, I will not tell you about this today because we have published enough works, and if you are interested, you can read. What happened is that during this time when we were trying to elucidate how do the beta-1 subunits interact, what is the interface of interaction, we did experiments to understand how is the mechanism for this adhesion. The works with the crystallization appeared. So now, in this moment of the work, we could consult the three-dimensional structure of the sodium-potassium ATPase, and we learned a lot about how is the alpha, how is the beta, and the gamma subunit molecular structure, okay? So we saw that the beta subunits of the pump form all the beta subunits, the three isoforms, beta 1, 2, and 3, and also the beta subunit of the proton pump, make a family of proteins that is different from other known adhesion molecules, but that are suggested to be adhesion molecules because of the structure, okay? But also we had shown that beta 1 is an adhesion molecule, and there was already in the literature evidences that the beta 2 subunit is an adhesion molecule. So now that we have more information about the three-dimensional structure of the beta subunits, we could make questions about the adhesion property of this family of proteins. That I must recall that the only P-pump that has beta subunits is the sodium-potassium ATPase. The calcium pump and other pumps of the P-type family does not have it. So something special this subunit has to do with the sodium, and there is obviously the evolutionary problem. When did the beta subunit join the alpha subunit during evolution, and what was the aim of this joining? So we suppose that the reason is that this subunit, the pump, is functioning as a recognition molecule. It needs to recognize where and with whom it will contact in order to realize its specialized function. Okay, so I skipped one, this one. Okay, so the beta 2 subunit was reported years ago by the group of Melita Schachner as a adhesion molecule on glia. And while we were working with the beta 1, we always, in presentation, the students with the thesis always said there is an evidence that the beta subunit is an adhesion molecule because in the brain it already was shown that it is an adhesion molecule. So this was like a dogma, you know. And now that we show the beta 1 is an adhesion molecule and how it interacts and so, we were again interested in this subunit, and we tried to see if there is a possibility that this subunit isoform also makes homotypic interactions as the beta 1. So what was known in this moment is that this beta 2 isoform is expressed in glial cells during the development of nervous system and also in the adult, and it regulates adhesion, neural outgrowth, migration, and functions in the neurons. And here I put two experiments from Antonicek in 89 and Antonicek in 87, where they use antibodies specific for this molecule, adhesion molecule, and show that it interferes with the adhesion between neurons and astrocytes, but not between astrocytes. And I will drink a little bit afterwards. So this is a classic experiment where you can use antibodies and assay for cell-cell adhesion. And if the antibody inhibits the adhesion, it means that the adhesion is taking through this adhesion molecule, okay? So with these experiments, they concluded that astrocytes that express the AMOG molecule cannot do homotypic interactions because the antibody does not inhibit these interactions, this adhesion. But it do inhibit the adhesion between astrocytes and neurons. These neurons are cerebellar neurons from early newborns mice. So here they concluded that this interaction must be heterotypic, which means that it has a receptor on the neuron that interacts with this beta subunit. Okay? And another experiment later, they used liposomes where they incorporated the AMOG, and they assayed the interaction of the liposomes with neurids, and they saw that the liposomes are adhering to the neurids of these neurons. So this was another way to prove, and they did many more experiments. Altogether, they concluded that the beta 2 is an heterotypic adhesion molecule. So this was the dogma or the paradigm that we had in mind during all these years. But once we saw that beta 1 is an homotypic molecule, we asked ourselves if beta 2 can also bind itself. And this is what I'm going to tell you in the next slides. Okay, so where is beta 2 expressed? There are about 5 or 6 different papers that show expression in different preparations of the brain. And the consensus is the beta 2 is expressed in astrocytes, but not in neurons. And this scheme is showing us that astrocytes express alpha 1 and beta 1, alpha 2 and beta 2, and neurons express alpha 1 and beta 1, and alpha 3 and beta 3. Okay? So one should not expect homotypic interaction between beta 2 subunit if it mediates astrocyte neurons interaction. Yes, I made myself clear? Okay. So the paradigm is that beta subunit is expressed only by astrocytes and not by neurons, and that astrocytes do not adhere to each other because of the experiment of Antonicek, and therefore beta-2 is an heterophilic molecule. This work of Zhao, it's a recent work from 3 years ago. They were sequencing messenger RNAs in different brain cells, and they saw again that beta-2 is a messenger RNA is practically expressed. I don't see from here, but this is the column from beta-2 in astrocyte. Okay, so there is no doubt that astrocyte express beta-2, but let's see what happened. Okay, to my surprise, I was reading the work of Flitan. She was a student in Sigrid Langham laboratory, and they were studying in a preparation of cerebellar granular cells in a culture and in microsomes from the brain, the expression of the 3 subunits of alpha and 2 subunits of beta. And as you see, both the microsomes of cerebellum and the culture of neurons express beta-2. So it seems that the only neurons that by now are shown to express beta-2 are the granular cells from cerebellum, and they express it during development, in the first days of postnatal development. So we decided, okay, so there is a chance to have homotypic interactions in the brain, so let's study. We realized various in silico experiments and studies, analysis, and we modeled the beta-2 because there is no crystal structure for beta-2, but we use the beta structure of proton potassium ATPase, which is homologous to the beta-2 subunit. And we modeled the beta-2, then we did docking, and we selected a dimer which is in a position of trans, which means the extracellular of one beta-2 is interacting with the extracellular of the second beta-2, as if they were in 2 different cells. Okay. So, and then we analyzed their interface, and we saw that there are at least 3 out of the 7 or 4 sugars out of the 7 N-glycosylation sites of the beta subunit in the interface. And we also could detect these hotspot amino acids in the interface. Later, we oh. No. Okay. Then we did the molecular dynamic simulation of the both dimers just to compare. And we saw that indeed beta-2 can make a dimer, and in this video you see the movement of the principal component, the first principal component of this interface. And we concluded that indeed beta-2 subunit is a homophilic adhesion molecule. We published it, and we were no, sorry. We published it, but of course we had to show that also not just in silico, but also in vitro and with cells, we can reproduce this interaction. So we transfected CHO cells with the beta-2 subunit. We created a stable line that was tagged with yellow fluorescence protein, as you see here. And when we treated these cells with tunicamycin, as you can see, it's too small, but you cannot see, but you try and you believe me. The beta subunit is removed from cell-cell contact and is internalized. We did an assay for cell aggregation because we saw that these CHO cells acquire epithelioid form when they are in culture. So this wanted to say that they probably make cell-cell contacts. We did a cell aggregation assay, and as you can see here, both beta-1 expressed in CHO cells and beta-2 aggregate. And when they are treated with tunicamycin, which inhibits the formation of N-glycosylations, the adhesion is inhibited too. So we concluded that cells expressing beta-2 make aggregates, and it depends on N-glycosylation. And this was included in the paper of Luisa. And the other experiments that Luisa did is a pull-down assay. We said, okay, the cells in CHO, they are adhesive, but how we can not be sure that this adhesiveness is through beta subunit. Maybe it induces another adhesion molecule that could be the result. So we tried to do a pull-down assay in vitro. We tried two different modes. Once with the bite as beta-2 YFP, and the prey was native beta-2 expressed in different cell lines. And none of these interactions were, we were able to reproduce in vitro. And also we did with transfected beta-2, and none of the pull-down assays really gave us positive results. We were ready to say, okay, beta-2 doesn't know how to do homophilic interactions, but we decided to do, we designed another experiment where the interaction is occurring between cells, because the pull-down assays are on the nickel beads or Cephalros beads. When you extract the cells, you get an homogenate, and you assay for the interaction on a matrix. In this case, we said, let's assay for the interaction in the real cell. So we co-cultures MDCK cells that express YFP tagged beta-2 and 6-histidine beta-2. And when we extracted, now homogenated this co-culture, the mixture of the two cells, and then pull them on a nickel beads, as you can see here, diluted fraction of this nickel assay brought or pulled down the YFP tagged protein and the 6-histidine protein. And then we were happy, and we could actually include it in the paper and say with more confidence that indeed beta-2 is capable to do homotypic beta-beta interactions. And of course, this is in a heterogenic system in CHO cells and MDCK cells. But what happens in the brain? Okay, so what we are interested to do now in the future is exactly this. Try to reconstruct this interaction, but now with astrocytes and neurons, and see if we can detect this interaction with cells that are coming from the nervous system. Okay. Now, this, how am I with time? Okay. This paper is the Litan paper from 219 that I told you before. And as the final figure of this paper, in which they try to show, they demonstrate a functional interaction between the beta-2 subunit and Merlin, which is regulated by growth factor signaling in cerebellar granule cells. And this is the paper where I took the Western blot with the 3. And in the figure, they illustrate this that caught my attention, because they talk about a switch that beta-2 is involved in, where it can be function as an ionic sensor via the alpha subunit, as a chemical sensor via the EGF receptor, and as a cell-cell contact sensor. And they illustrate a straight relation contact between beta-2 subunits that are doing all of this effect intracellular in the neurons, and another beta subunit in neighboring cells. So they assume that the beta-2 is actually doing an homotypic interaction with another cell, but they do not say nothing about this part of the scheme, no? But I think that now it's not so difficult to broke with the paradigm, because there are evidence that support the possible interaction, homotypic interaction of these two isoforms. And as I tell you, what we are thinking now is that during development of the cerebellum or the neocortex, where the neurons move and migrate from one layer to form the differentiated neuron layers. And so it was shown that in this process is where the interaction of AMOG between glia and neurons is important. So now we would like to try to see, because nowadays there are much more techniques with fluorescence, with microscopy, with other techniques that you could do many experiments that on those days they could not do. So we are planning to do something to see this migration or movement of neural cells and try to detect the interaction, the homotypic interaction. Okay, so this is for the future, and as Rajini said, we are hiring. So if somebody wants to come and do his project in Mexico, is welcome, or postdoc. And now our actual PhD student, Christian, is studying the possibility that there is indeed heterotypic interaction. So the homotypic interaction does not exclude heterotypic interaction between astrocytes and neurons in adult. Okay, so I asked him to look at the databases. He entered to the BioGrid page and looked for any reported interactions with the beta-2 subunit. You know that now everybody knows interactoma, metaboloma, avilloma, and and there are a lot of information in the databases that one can use and are useful. So what we found that indeed there are two big works of interactions where there is a list of about 17 proteins that are reported to interact directly with the beta-2 subunit. We looked which of them is a plasma membrane protein, and that is reported to be expressed on neurons, and selected them as candidates to be the receptor. So the proteins are, it's too small. I was not aware that it will be so. Okay. So this is the red of interaction where ATP1B2 is in the center and different proteins that are reported. The ATP1A3 is the alpha-3 subunit, which is logical to find an interaction between alpha and beta subunit, and another proteins. And the one that we choose to continue studying is the tetraspanin 31, which is a 4 transmembrane protein that is part of a big family of tetraspanins. And as you see, it's a plasma membrane protein, and there are reports that it is expressed in neurons. So now Christian is modeling this protein because there is no crystal for this protein. He modeled the protein, then he did docking with a beta subunit, but afterwards he realized that there are reports that inform that the tetraspanins make dimers in the plasma membrane. So again, he had to dock 2 monomers to find dimers, and he chose the model that predicts interaction between transmembrane 1 and 2, as it is for other tetraspanins. And also we modeled a dimer of the sodium potassium ATPase, but with alpha-2, beta-2, and gamma subunit. And now we wish to do the docking and then the molecular dynamics, but this is more complicated because now the information is huge, and we are looking for or the right platform or the way to ignore the transmembrane domains and so, and just work with the extracellular domain in order to try to minimize the size of the data and get information about this. But of course, meantime, we are trying to get tools that express tetraspanin 31. So we transfected HEC295 and CHO cells. I don't know why the, no, okay. And as you see, we have tagged them with a green fluorescent protein. And now Christian is planning the pull-down experiment in which we have already cells that express beta-2, and now we will have cells that express tetraspanin. And the first approach will be to, again, do the pull-down experiment in order to assay if they can associate in vitro. And that is all I prepare for you for today. I thank you for listening. I hope you could follow my ideas because I didn't show many results because we are exactly in this transition of an old project that we feel we are okay with it. Now we want to make new questions and new approaches and try to elucidate about this isoform. So thanks. This work was done in the Sinvestav. These are the guys from the lab who worked mainly on the beta-1. This is the Marquesa in Mexico City, so you are invited to come and visit and take a ride. And here we were celebrating someone of the kid's birthday. And that's all. If you have questions, I'm ready to answer.
Thank you, Liora, for interesting talk.
Thank you for a very interesting talk. I mean, it was particularly interesting for someone like me who is interested in brain development. My question is about the sort of in vivo localization of these beta molecules. Do they, present always near or attached to the alpha subunit, or they can be sort of, present separately, doing its own function. So are they these,
All assume that they are always with alpha subunit, but because there is no evidence ever, nobody could demonstrate that the beta subunit could be in the membrane alone. So always, although I talk about, this is a very important question because the students can also be misleading. Always when we talk about the beta subunit, it is obvious that it is accompanied by the alpha. Okay? If it is in the astrocyte, it's alpha 2 with beta 2. Okay? So all the physiological role of alpha 2, alpha 1, so on in the brain, in astrocytes, in neurons, so is very much studied, and we understand a lot of things physiologically and the relation between but with the beta subunit, we have no idea what happens there. Okay? So the group of Schaffner years ago, they show that this is it functions as an addition molecule. But really there is not much information what is the function, what is behind this interaction. Okay? So Litan actually is trying to show that it is a receptor that transmits information, signaling information inside the cell that regulates insulin, the neurons. But there is no much information about this part of the.
Thank you very much. Thank you.
Hi, Yoda. Thank you for your speak. I love to understand better about the beta adhesion. You showed like a complex with beta 2 and alpha 3. And I don't know if I think I didn't understand very well. What is you are suggesting if the alpha 3 is associated to beta 2, if you can clarify for me again. Yeah.
This would not work. Hartlin was in 2017 and 21, did two big works of interactions between CHO cells and he used as BITE all these proteins and then analyzed with mass spectrometry who are the proteins that interacts with. So he finds in this system that ATP1A3 interacts with beta 2. So yes, the classical couple is for beta 2 is alpha 2 usually, but for some reason in this system it interacts with alpha 3.
More questions?
Very nice talk. So can you comment more on the sugars? You show something there that there are 5 sugars. Is that what is giving the specificity for beta interaction? And
yes, I can talk about it, of course. First, all neural cell adhesion molecules are glycosylated, and it has been shown that the sugars are important for this interaction. Mm-hmm. 1. 2, the question is, if the sugars are part of the mechanism of interaction, if the adhesion molecules interact via the sugars, or it just needed to stabilize an adhesive conformation. So in the molecular dynamic simulations that we did in the analysis, it is a paper that we just sent to publish, but we have not answered yet. But in this work, we are showing that the role of the sugars in beta 1 and beta 2 is different. In beta 1, the sugars do not participate in the interface. So probably they are needed just to gain an adhesive conformation. And in beta 1, they do participate, and they are needed to make a more stable interaction. Yes.
So, and again, just to go back to a previous question, if I can do so.
Yes.
You have never seen beta alone in the membrane.
There is one work with insect cells.
I know. That's why.
That you are a co-author.
Yes.
And in this work, they managed to express the beta subunit alone. But this is an artificial system.
I know.
The cell has a mechanism of biosynthesis that ensembles alpha and beta since they are
in the ER.
Yes. Yeah. So, and they do not get to this is already well established that they are not getting to the plasma membrane if they are not ensembled.
Yeah.
But there is another work of another guy that I don't remember his name now, that shows that the internalization of the recycling of the protein from the membrane is in this process, they can disassemble, and each subunit is internalized via another mechanism. So maybe once in the plasma, there is a situation where they can dissociate. But nobody has shown this.
Thank you.
You're right. Learned so much. Thank you. Are there any mutations in the extracellular domain of beta subunit associated with any disease?
Okay, this is another thing that we were talking the other day.
Okay.
There are no mutations reported for beta subunit at all, or disease related with mutations. But yes, there is a lot of information for beta 2 in relation with cancer, with gliomas and glioblastoma, and which means that beta 2 is considered as a tumor suppressor protein, because when the cells are transformed to cancer, they lose or they down-regulate the expression of beta 2. And if you transfect glioma cells with beta 2, they revert. So this is interesting. And also there are reports relating it with malformation of cortex and degenerative disease, Alzheimer and so. So this protein is important because it mediates neuron astrocytes interactions. And it, in adult, in the brain, it localizes in the in astrocyte in the how do you call this, where it interacts with the blood vessels. Yeah. There is a name for it. Mm-hmm. And in the plasma membrane. And the interesting thing that I didn't tell you about, because there's too much information. In the astrocyte, the sodium pump is not alone. Is always in a complex with more transporters and receptors, with glutamate receptor, with monocarboxylate transporter. And I think that this is the mechanism that impairs the homotypic interaction of beta 2 between astrocytes, because it is compromised, structurally talking, with other proteins in the same membrane. So this extracellular is probably not available to do beta-beta interaction. This is my hypothesis.
Questions? I have a question about so it's ignorance, but I've never seen before an interaction. I know about the interaction of beta-beta subunit, but not the interaction of beta subunit with an intracellular protein. So you said there about Merlin, the protein Merlin, because we always understand that the interactions are with the alpha subunit. And so
the sodium pump in the astrocyte is interacting with other proteins in the same membrane, not in trans, but in cis.
yes, but in beta, with the beta subunit or the alpha?
Beta, and then with the monocarboxylate transporter. The beta subunit of the monocarboxylate transporter, which is vaccine, CD147, is the IgG-like addition molecule, and there's a lectin that binds the sugars of the beta 2. Mm-hmm. So this is why I think that this beta 2 is not exposed to water. But intracellular, there are no reports for interacting molecules intracellular with the beta subunit.
Oh, the Merlin proteins? Yeah.
The Merlin is a new case.
A new case, okay. Thank you. No more questions? So thank you, Leora. And I would like to thank the speakers for today. Today is a small session, and this afternoon are free for you. And tomorrow at the same time, so we'll have the whole day with the last session of presentations here. Thank you for all. Have a good day. Have a good lunch.